Okay, let's start out. Excuse me?
What's the
The Lady Tasting Tea. I'll bring a copy of it next time. It's a history book of the statistical revolution. All very fascinating. There's a chapter called The Confidence Trick. And it's very interesting, the dialogue that happens. And so I want to talk about that in detail. I'll refer to the book, and then I'll read the actual passage to you next time, because I think we'll be on the same lecture. Okay, I want to point out that I had made an error last time. Eric was right. It's a beta binomial is the posterior predictive distribution, obviously, once you think about it and you're not confused for a second. I probably should have just worked it all out and seen it. And so how do you do that integral? Bunch of beta functions. So when you come up with the posterior predictive for the binomial distribution working under a beta prior. So what's that distribution called? Beta binomial, people call it. It's the mixture of the two things. And so we'll be using that language as we go, the mixture. So the posterior is acting as a mixture distribution over the binomial distribution. You're integrating them into each other. So it's called mixing. Makes sense, right? So that integral is a big mixture. So it's mixing things up, it's averaging for you. Averaging one distribution over the other distribution. Very cool. I had corrected my lecture. Let's see if I can get started. What this key does. What can x tilde be? Got to live between 0 and n. So counts. The original x came from a binomial distribution. It lived between 0 and n. You're going to predict something that will live between 0 and n. So you think it might be a beta binomial? It is a beta binomial. That was the part of the lecture I made a mistake. So go look at Wiki, look up what a beta binomial is. I've included in, I've updated the lecture. I have editing skills at my computer. So I snipped out a minute of me telling you the wrong thing. Let's talk about intervals. So I'm going to move on, play around with problems. Okay, so that's just an amendment. So go back, look at that. Half of what I said was correct. Eric had it correct, so he deserves a credit in the movie. Have your agent contact me, and I'll get that in there. Look for your rates, make sure that you can afford it. So once we write your name down. Okay, I want to come back around to intervals. It's where we left off last time. Jess, are you carrying a copy of The Lady Tasting Tea by chance? The book.
The book?
Yeah. It's okay. Just trying. Seeing if anybody has it. It's a good passage that relates to what we're talking about right here. Intervals. We're going to go through Bayesian intervals, but I want to compare and contrast against frequentist intervals. Now, I probably should already rephrase that because Bayesian can be a frequentist. So that's not a fair thing to say, but they're not obliged to be a frequentist. And I'll try to explain that as we go. There's a passage I want to read to you from The Lady Tasting Tea. Mohammed, are you carrying a copy of The Lady Tasting Tea? There you go. So we've been reading it in our department in statistics. So it's a good historical overview. I forgot how much it excites me to think about what people have done in the past, why they did it, what the arguments are, because when we learn things, it's kind of like gospel. It's like, here you go, know how to do it. And there's been a lot of discussion, argument about how to do things. Confidence intervals, we were kind of talking about this last time. We looked at an example. And so basically, you have a sampling distribution, you want to know the beta. I'm going to think of beta as a one-dimensional scale. But you could do this with regions. So you could extend the concept of interval to region, if you would like. And I mentioned, usually do not see frequentists do that. And so why? It's hard. You know, what's their asymptotic distribution of the joint space? So it's hard. It's not impossible, but it's hard. Bayesians, you'll see, do this quite often because our intervals come directly from our posterior distribution. So you're just kind of picking out a region that has a certain amount of mass in it. We'll discuss that in a number of details. Confidence intervals are random intervals. So I just want to point out this right here is a function of the data. So these function of x or n data points. Okay, those are coming from this right here. And so I want to create an interval such that it covers the truth with probability, whatever I declare alpha to be. So I think instead of always saying alpha, sometimes I'll say 95 because it registers in our brain real quickly. 95 is a little bit arbitrary. Well, it's a lot arbitrary. Since arbitrary is 94 and arbitrary is 93. So anyway, we have 5 fingers on our hand. That's why we actually round to 5s and 10s. So it's an arbitrary thing. If we had 4 fingers per hand, we would make different decisions. We'd be working at base 8. And so it'll change all your thresholds. So it's kind of interesting. You know, I think about when I see people, you know, kind of making these arbitrary rounding decisions. I have friends that when they tank up their car, they have to round it to a penny. They're like, it makes sense to do that, I like it. And it's like, wow, if you had 4 fingers per hand, you would fill up your car differently. So I always fill mine up until it doesn't take anymore. That's why I'm there. So anyway, 95% is a bit arbitrary. We can think about that as we go. But it's a standard that people like to think about. Have to do something. Fisher basically said 1 in 20, 5% is a reasonable threshold for things. So reasonable, not much defense there. So just declares it reasonable. Maybe it is. So these are functions of all of these data points right here. The idea of this interval, you know, what is random here? It's the interval itself. Theta is presumably fixed in the classicist paradigm, or the frequentist paradigm. Again, there is overlap between frequentists and Bayesians. So give me a little bit of room when I'm discussing these groups, because there is intersection. So the idea is this. If I ended up getting, let's just say I put K on here, and I got K different data sets. I'll let K go from 1 to cap K. So this cap K is the number of data sets I'm going to go out and collect. So this is the idea of a confidence interval. You don't actually go and collect these K data sets, you collect one of them. But the whole idea here is that you have your true theta, and I'm going to put a K on all of my bounds right here. So that I have an interval for each one of these data sets of size K. The idea is that your different intervals, let's just say this is theta, this is L, theta, K, we're all saying 1, and U, theta, 1. So L and U are for lower and upper bounds. I'm thinking about this as like this nice continuous set. You know, if you're bimodal or something like that, you'd be inclined to take 2 different intervals. And so you wouldn't want to cover the middle. We'll talk about that as we go through different examples, but keeping it all pretty simple, the way we usually learn it in Stat 101 class. So it's just this connected interval. So the idea is that these different intervals that you would construct, L theta 2, U theta 2, would cover the truth with probability alpha. So 95% of the time, these intervals would cover the truth. So if I got these K different replicated data sets, I could construct cap K intervals, and alpha With probability alpha, those intervals cover the truth. So that's the idea. Very puzzling concept. What is random? So the idea that everybody was discussing, and this is what I want to read you from this. It's kind of a fun read. It's just a historical overview. Is how much disagreement there was about that idea when it was first introduced. So basically, Jersey Neyman, Fisher, they were coming up with this idea. And so Fisher was basing it off of likelihood. So he said, well, let's just look at the likelihood and carve intervals out of this. That's not a probability distribution. Bayes does something to try to transform it into a probability distribution. But likelihoods are not probability distributions. The whole gripe was, what is this a probability of? So what's probability? It's random, something's random, but it's of these little intervals, whether or not they cover the truth. What does that mean about the parameter itself? That's hard to digest. So when your Stat 101 teacher talked to you about this, they said it makes sense. Just say it right. You know, alpha is the probability that my random interval covers the truth. Don't say it any other way. You know, or else you lose points. If you say it's the probability that this interval contains theta, that is what you get dot points for. Theta is not random here in this sort of conceptualization. And so this word probability right here troubled people. Probability of what? It's not the probability of the parameter. We're trying to talk about uncertainty of that parameter. Some people will talk about these intervals and say, look, there's a one-to-one correspondence with a hypothesis test. And so it's giving me a region of parameters such that I would not reject my null hypothesis. Everybody's heard that terminology. We'll go through decision theory and hypothesis testing soon enough. But sometimes people like to talk about these intervals as having a correspondence to that. So the mathematics people go through is called pivoting. So if you ever had an inference class, maybe you've seen that. So the idea is to pivot around your data that's random. So people try to change the word. So Fisher, when he was just basing his intervals off of likelihood, which seems like a really good idea if your data's normal. So remember what the Bayesian does, they use the flat product. So essentially we're basing our inference off of the likelihood, but we formalized it through a limit of conjugate priors. And so they have some good properties for us. Fisher did not like the Bayesian mindset, especially when he was talking about this at first. So he said, just use the likelihood and draw where you think the parameters are. They're going to be in the dense part of the likelihood. He called that a fiducial distribution. It's not a probability distribution. What does that mean? Nobody knows. And nobody knew. There are papers that are written even to this day. I saw one a couple of years ago called the correct fiducial argument. The correct fiducial argument, I think, is Bayes. So, one word paper. They go on and on. I don't think they agree with that per se. Nobody actually does fiducial statistics anymore. People do Bayesian statistics. Fisher didn't like talking about priors. And I think everybody in this class can kind of understand that. It's like, it's kind of got a stigma. I'm going to elicit my subjective judgments and then also weigh it with data. I think that's what we do as statisticians, but there's also priors that try not to inform that space too much. They have minimal impact on the inference. We'll be talking about that as we go. Kind of seen that through a couple different inferences, a couple examples. And so, people didn't exactly like the fiducial argument either. So instead of talking about probability, they talk about confidence. And the article or the passage I want to read you basically says, I don't know what this confidence thing is, but I do know I'm being tricked. This confidence trick. So what is this thing? What is this probability? And so it's certainly not about the parameters. Now, a credible interval, this is what Bayesians play around with. This is a belief interval. Tells you where you think theta is. Okay, so it has a probability distribution on this. Where do they get the probability? By a Bayesian theorem, a posterior distribution. So, the Bayesian interval, if you say you've got a 95% interval, you're saying you believe the parameters in there, the probability 95. Okay. So, a 95% interval, suggests the parameter. And the parameter in the Bayesian paradigm is random. 95% interval suggests the parameter is in the interval with prob 95%. Or you can slide alpha if you want to talk about it more generally. The kicker is, in the example that people always talk about in Stat 101, the normal example, the Bayesian, the typical Bayesian, and the frequentist come up with the same interval. And they have two different interpretations. So just think about this example. Xi's come from a normal distribution. I'll say this is parameter. Mu is theta in this case, just so we can stick with the same notation. I'll say sigma squared is known. Makes everything easy. If sigma squared isn't known, then you estimate it and you move to a t distribution. So every Stat 101 student knows it. Now you understand why after going through that integral so many times. And so if you were to do this in the classicist paradigm, you are solving that exact same integral we solved for the Bayesian posterior when we integrated across phi. So example, everything's normal. The frequentist confidence interval is just this thing, x bar plus or minus 1.96 sigma over root n. That's what you would do. You knew sigma, you just plug it in. I had made another error last time. I put 1.96 down, and I was suggesting you estimated sigma. It wouldn't be 1.96. It would come from a T table, and I don't know all of those numbers for all the different ends. So I don't know off the top of my head. If you go over like 30, 31 or something like that, it gets close to 1.96. So this is your control limit. So if you standardize all of your data in this case, what you're essentially going to look at is x bar. You're going to look at a standard normal, and you're going to standardize everything. Let me just say it like this. Well, I think we've all done this, so I think I'll stop with the 101 lecture. But the classicist would do this, the frequentist would do this, and this is the random bit. So that's what's random. So that's what you're pivoting around in inference class. You take more theoretical class than this. Okay, so the lower bound is when you subtract, the upper bound is when you add. So interestingly, the Bayesian interval is also x bar plus or minus 1.96 sigma over root n. Our posterior distribution is centered at x bar. And we know what the standard error is of the analysis. So this would be your 95% interval. So the classicists and the Bayesian are using the exact same distribution, but they think about it differently. So the classicist interval is how gamma lies in that space, probability distribution of your test statistics.
Is this valid for any sort of prior or for the reference?
Ah, very good. Yeah, absolutely. Has to be said. Under pi theta proportional to 1. Very good. So if you use this reference prior, we use the same distribution. Saying that, I really like this because it tells me my Bayesian interval, it's a belief thing, and I can say that's where I think theta lives. And if you're into frequentist stats, I can say that's an optimal covering interval. So you get both worlds, best of both worlds here. So that's kind of cool.
If you're always using the improper uniform prior, that basically amounts to reweighting your likelihood just that it adds up to 1. And so when why would Fisher not just say, like, okay, just hey, you know what, just reweight the likelihood. It's like case, but with all uniform improper priors.
Very good question. This is why we're having our history discussion offline. Well, we had a book reading. We've got a little book reading club. If you guys want to pick up this book, The Lady Tasting Tea, I recommend it. They join in our conversation as well. Fisher was stubborn. So he was just stubborn. Couldn't be wrong about anything. So I think what people did is they said, that's Bayes, what you're doing. And he said, absolutely not, it's not Bayes. I don't care what you tell me. After a while, when Fisher kind of aged out, he ended up saying what I'm doing was probably tantamount to Bayes. And so he admits it later, but it doesn't detract from the argument existing for a while. A lot of confusion. I don't know, everybody wanted the credit for everything. They wanted to see it their way, not like anybody else, not follow anybody. I'm going to build my legacy like that. I think that's the mindset. It's hard for me to appreciate because I just don't think about this stuff like that. You know, we're supposed to just be helping out science. So if we get some credit, that's cool. I'd like it to go around. But Fisher didn't feel that way. So that's what I think the answer is. Saying that, we have agreement, and that's nice. So let me show you an example where we have no agreement. Don't have agreement in this example. And so this goes back to what I was saying, probability of what? What's this a probability of? And so this example shows you no big deal, it works out great. And so I like it. And so what Fisher was using, this interval, regardless of how we thought about it, we're all using the same interval. And so if everything, we're talking about stuff on average, we're employing the central limit theorem, we're using an interval just like this. But there's a lot of examples where things aren't so pretty. I want you to remember that the data is symmetric with theta. And so that's why we have this agreement right here. And so that symmetry plays a big role. A lot of examples are not like that. So I think everybody was talking about this example for like 100 years. And so it was, I know I want the answer to be. You know, but now we have lots of examples to think about. Lots of smart people have said things about this. So this example comes from a paper, and it's entitled, Could, went first. Fisher, Neyman, and Jeffries agree. These are three people. So talk a little bit about Fisher. Neyman does something totally totally different from Fisher. And they get into a big argument. Jeffreys is an objective Bayesian. Okay, so he's developing the Jeffreys prior. We'll talk about that soon as well. The answer to this question is no. I'll put this paper online so that you can follow the example a little bit more thorough. But I'm going to walk you through their argument. The answer to this question is absolutely never, not on anything. It doesn't matter what it is. So, it's like, is ice cream good? Somebody's going to fight with the other one. Just take an oppositional statement. And that's how it was. Here's my example. Kind of a little bit weird, so I want us to think about it for a second. I'm going to say my distribution is going to be xi is going to be equal to either theta plus 1 or theta minus 1. And each happens with probability 1/2. Theta is unknown. You might think you know a lot about this distribution. You do. It's a Bernoulli coin flip. But I'm not telling you what theta is. You don't know what the realizations look like. I'm telling you what the probability is. And so this problem is different than you're used to dealing with. Theta is unknown. The goal here is to predict theta. I said predict, learn it, infer it, whatever you want to say. Estimate it, figure out what it is. So that's what we want to do. I'm going to say I goes from 1 to 2. You're going to get 2 coin flips. That's all you get. That's all you get to see. So if you got to see a lot, you would learn theta real quick. So keep in mind, this is just an example to kind of highlight the differences between what Bayesians think and what so-called frequentists think. Okay, so I'm going to give you a confidence set. Just going to give this to you. Now, in my example, I'm not going to build an interval for theta. I'm going to give you a set that covers theta. So it's not a connected interval. The nature of this problem doesn't translate to giving you a really good connected interval. And so it leads you to want a set. Okay, so you don't need just intervals. They can be disconnected things that cover the truth with some probability, but they can be sets. Okay, so the only thing important about an interval is the context of the problem where it's like continuous. You want to think about it that way. Okay. This is my confidence set. Function of the data. Let's say there's 2 possibilities here. That's what makes this a set. I'm going to give you x1 plus x2 over 2 if x1 is different from x2. Okay, that's one possibility. So I'm going to look at this condition. If x1 is different from x2, I'm going to report this answer back. Or I'm going to give you x1 plus 1 if x1 is equal to x2. Okay, so I can plug x2 in there too, exact same thing. I want somebody to think about this for a second and tell me how often this covers the truth. So there's a true theta out there, and sometimes that confidence set hits the truth, and sometimes it misses. So let's just think about this real quick. Unless Mohammed's got an answer. Yeah, I've used this as a qual question. So, That's right. Good job.
Why are you only doing x1 plus 1?
What's that?
Why are you only doing x1 plus 1? I mean, there are two cases here.
Yeah, you're right. So this was arbitrary. But it's an answer I'm going to give. Okay? So I agree with you. You probably want to think about x1 plus 1 as well. So we'll get there. So I'm just throwing this out there. How often does this cover the truth? Let's think about this one. Top thing. If this is true, what is that number? It's theta. That's theta. Why is that true? I'm going to say this is theta plus 1 plus theta minus 1 divided by 2. That couldn't look any worse. I know that it's one of them. I've labeled them. So, but I add them together. Plus 1 minus 1 cancel. That's 2 theta in top. Divide by 2, that's theta.
Why is so sorry when you get the fun?
Say what?
Why don't you relate? I mean, if the case x1 is different to x2, okay, because it's the only two values possible.
Yeah, it takes a while to see this problem and to think about it. So keep drawing pictures until we all understand it. But people are slowly catching on to what's going on in this example. So if this happens, x1 is not equal to x2, I get theta. This is theta 50% of the time. That's the arbitrariness. So I could have subtracted 1. If that wasn't theta and I subtract 1, that one's theta. How often does this happen? %. How do I know? That's 1 half. So I flip a coin. Maybe I get that. I flip it again. What's the probability that they match, or that it's this other one? 50%. And vice versa. So that means this happens 50% of the time. So if somebody help me out, what's the confidence level? This is my confidence set. It covers the truth. How often? 75%. 75% is the answer. This is theta 100% of the time. This is theta 50% of the time. So I've got 100% happens with probability 0.5 plus 50% times 0.5. Those are the 0.5s. That's 75%. So this is 75% confidence set. It's true. That's what it is. It covers the truth. So it's perfectly frequent test. This is an exact interval, too. I don't have asymptotic error. So it's not like it's kind of close to 75%. If I asked you to conduct a simulation study and you weren't hitting 75%, I would say you have an error in your code. So it's got to be there. You know, I mean, I can understand little rounding and stuff like that, but you need to do it a whole bunch of times. That's 75%. The first time I try to do this, if I just do it once, 75%. So what we report in the purely frequentist confidence set paradigm is I would report this thing a priori. So a confidence interval or set is an a priori procedure that I have a probability that it covers the truth. Okay, so that's what it is. So before seeing the data, no, people don't like this sort of stuff. I can do that too, to the frequentist. Before seeing the data, you've constructed a procedure that has some mathematical probability of covering the truth. And that's what confidence is. So some people might not sit very well with this answer. So here's the problem with this. And I think all of you would be ready to jump out of your seats and say, I would never do this. This is stupid. But this is the whole point about this question of probability, and what is this a probability of? It's the probability that this random set is going to cover the truth. So that means I report this thing to you. So I'm going to give you one of these. And every time I do it, I'm going to say 75% confident. Anybody have a problem with that? So I flip 2 coins. I happen to see this. I report this back, and I say 75% confident. Stupid. It's ridiculous. So if I report this, I say 75% confident. Yeah, it doesn't make any sense. You wouldn't do this. I wouldn't like this answer if somebody came to me with this. This is what the gripe is about. You can construct other examples that are similar to this. You can come up with examples where Bayesians almost agree with the frequentists, if not entirely agree in terms of what they report. All they're saying is things different. A Bayesian would not report this. So the paper that I'll post online discusses a frequentist approach for getting this right. And it has to do with being the conditional frequentist. And so what you're allowed to do is condition on ancillary statistics. And so the ancillary statistic of interest might be the difference between the xi's. And if it's 2, then you do something. If it's 0, then you do something different. So the paper discusses it's hard to construct that in general. You don't know what the right conditioning statistic is. If this is over your head, that's okay. I just want you to understand the 75% bit, and this is a bad answer. So saying that, it's true. It's 75% coverage. But what you're reporting every single time is the confidence level, and that's not changing. And so let's think about what a Bayesian would do. So bad answer, but true.
To clarify, confidence level is 75%?
Yes, that's 75%. That's the confidence level. Yeah. So that's what they're always reporting. They a priori have a number they're going to report to you. A lot of times it's 95%. So how would you get 95% here? You could add some random point flips in the middle. And if they land a particular way, I give an answer. I can blend like that. People have proposed solutions like that, but it's not a good thing to do. Nobody likes that. So we'll leave that there for a moment, let you ponder it as we think about what a Bayesian might do. This is the first step that a Bayesian always does before they do anything else.
So it's prior to there.
Yeah, I would say no. So I don't do that step first. I do that second. That's the second thing I do. I don't know what theta is until I discuss its likelihood. So step 1, write down the likelihood. Step 2, now choose the prime. So I'd say every Bayesian, write down your likelihood function. If you don't write it down, don't proceed. So I've had a conversation with a couple of my students, and I'm like, show me the likelihood function, graphic form. And voila, there. So I can see now the computational here in this. Don't proceed without like plotting your likelihoods, thinking about your likelihoods. Bayesians are really just infatuated with likelihoods. And then they do this other thing that hopefully has fairly minimal impact. Under small sample sizes, you gotta do something. Okay, so what would you do? Step one, write down the likelihood. Step two, we'll think about the prior. What's the likelihood? This is the fun part of this problem. What is the likelihood for theta? Do me a favor, Mohammed. Come up here. Write it in this box. We're all gonna owe you a debt of gratitude for being brave and coming up here and writing down the likelihood function. We'll save this one first.
This one's more because you have here. X is 0. Theta plus 1 and theta minus 1. Basically.
It's the whole name of the game. If you're Bayesian, you can write down a likelihood function pretty quick. But we're doing this because I know it's a struggle. You want me to rescue you? Do you want me to rescue you?
Yeah.
Does anybody else want to give it a shot?
Wouldn't it be
Here, Mom, you have a seat and you come up and give it a shot.
I'm worried advance my handwriting is bad. So if I state it as the case of the product of the two possible values times their probability, it will be 1/2 times minus 1 plus 1/2 times theta plus 1. And in the case, it will be just theta.
Okay, that's an answer. So it's not right. So we need more help, but yeah, absolutely. I mean, bravo, fellow. So this is hard. Anybody else want to give it a shot? I'll take a whack at it. I know the answer. I think this is the whole thing. So I'm going to get rid of those. If you think about this, it's like, what's t right here? If I plug these in, the 1/2 in 1/2, it's like, what does that do? As theta gets bigger, this just blows this thing up. It's going to say infinite theta. Same with this, right here. This theta is the likelihood that I would pick theta to be infinity. So, and that's not how it works. Theta is a shift parameter in here, and so it should be shifting around the whole problem. So let's just remember the nature of theta. shifts the data space, slides it back and forth. Okay, the likelihood function looks like this. Proportional to. So I could just do this real quick. So f x1 given theta times f x2 given theta. That's it. So just product those two things together. So what is this? If you'd like, I could write down this in terms of a probability. So you can be thinking about it, and then I'll think about it as a function of theta. So what do I write down for this? Very tempting to do this. I've seen this answer a lot of times. A lot of people will write this down. It's a half times a half. And then you're like, oh no, there's no theta in there. So there's a restriction on this problem, and we have to include it. So this is 1/2, that's true. But then I also have an indicator function right here. This is an indicator, and it's going to indicate what valid ranges of the parameter are with respect to the data. So it's an indicator. And this says that x1 is equal to one of two things, theta plus 1, theta minus 1. So there's a relationship between the data and the parameter, and it comes through the indicator function. This is similar. This is an indicator function. x2, use the same colors here. x2 is, and I'll write down element, it's one of these two things. Theta plus 1, theta minus 1. These probabilities right here aren't doing anything that's wrong. So it's that indicator function. So the indicator function is a 1 if this is true, or 0 otherwise. So I'll just write down xi element of this is equal to a 1 or a 0. That's what I mean by indicator. It's a switch. If xi is one of these two things. And this is xi, not an element of those. We need to be able to plot this function to understand it better. So I think that's a really good place to leave off. But I want you to think about this and try to draw that function. If you need some help, do it on a computer. So I'll draw it for you next time. But there is information here, and the information is coming from this indicator function. Real quick, last question before we leave. What would you pick this to be? What's that? 75%. So this has to be a function of theta, something like that. So that's a number. I need a distribution on theta. I want you to think about this. It's a shift. So let's come back next time and draw out this whole solution. It's a very contentious problem. I'm going to put the paper online. You can read through it, and I'll bring in the late PCP and give you a 5-minute over the discussion. It's basically, this is a good example to understand why they were not so accepted. So, okay, that's it for now, guys. Okay, thanks, you guys. It's awesome. It's like kind of funny to like get up there, start writing something, make a mistake, and you're like frozen. Oh no. Gotta get used to it.
Why are we removing? But if you guys are probably trying to do the analysis.
Well, we'll look at it. So there is a little bit of a problem with the MLE in this. In one of the cases, the